Hi, and welcome to this poster presentation for the final year research project 1. My name is Lucas Yu Ping and Dr. Bezu Wong supervises me. The topic of my research is the Monte Carlo simulation of low energy electron beam propagation in semiconductor. First, a brief overview of my research and the rationale behind it. In this research, I'm interested in describing the paths of low energy electrons as they travel through different semiconductor materials. We know from the literature that these electrons will either do one of two things when interacting with the target material. They can experience reflection, in which case they'll travel back in the direction of the source, or they can transmit through the material. Regardless, we can chronicle the trajectories using a Monte Carlo simulation program. Subsequent to that, I can build a database to store and organize the results. We can then develop material recognition using this collection of information that includes quantities such as angular, spatial, and energy distributions of different semiconductor materials. One of the rationales for this research is the scarcity of studies performed on electrons at these energies. This encompasses the energy spectrum that is categorically under 1 keV. Therefore, through this research, I hope to provide some, if not more, insight into electron behavior at these energies as they interact with different materials. Stated here are the research aims. They are to simulate electron beam propagation inside semiconductor materials and to develop material recognition using the simulated reflectance database. As mentioned before, the relevant literature calls attention to the shortage of research focusing primarily on electrons at low energies. Therefore, we do not fully understand how these electrons will behave when they propagate through different target materials. Besides that, the literature has also shown reasonable verification of the results obtained using a Monte Carlo method, compared to the conventional, more sophisticated analytical approaches. Hence, the product of this research can be considered reliable and can therefore be used by other researchers. Thus, we hope to obtain a better picture of these electrons through a simpler, more straightforward technique that can easily be adopted in different research fields. For my research, I'll be adopting the methodology of a review article co-authored by my supervisor Dr. Bezu Wong in 2010 titled A Unified Monte Carlo Treatment of the Transport of Electromagnetic Energy, Electrons and Phonons in Absorbing and Scattering Media. Specifically, the chosen proposition is a continuous slowing down approach, or otherwise known as CSDA. A CSDA MC simulation considers the inelastic scatterings as continuous phenomenon and thus equates energy change to the distance traveled by the electron. The first step in the CSDA MC simulation is the initialization of the data. In this process, the researcher will input the properties of the target material, its geometrical dimensions, and the energy-dependent scattering properties of the electron beam. Distance of interaction is then generated, and subsequent, the electron is moved. The distance of interaction mentioned here refers to the elastic and inelastic scattering mean-free paths. If the electron is still in the medium, the amount of energy absorbed by the target material will be determined based on the distance traveled by the electron. In the wake of that, the electron energy is then updated. Next, the program will verify whether the electron energy is too small. According to the magnitude of the critical energy, definition of too small may vary from researcher to researcher according to the magnitude of the critical energy E sub c defined. The implementation of the verification process may also differ. The succeeding step involves determining the electron direction based on the elastic cumulative probability distribution function, or CPDF in short. However, if the electron exits the target material after the prior interaction, information on whether the electron is transmitted or reflected will be updated by the program. The fate of the electron, whether it experiences reflection or transmission, will be illustrated in the output window of the program. Shown here are the Monte Carlo simulation of electron trajectories in silicon and gold foils 1000 angstrom thick at 1 keV incident beam energies. These figures are shown for illustrative purposes. 10,000 trajectories are plotted in each example. Note how both the size of the interaction volume and its shape changes as we move to progressively higher atomic number materials. To sum up, more semiconductor materials will be simulated. Sufficient data shall be assumed when the common semiconductor materials have been covered. They include silicon, gold, germanium, copper, zinc, etc. The expected outcomes of this research consist of procuring the information on the different types of distribution from the simulated trajectories. Ensuing that, the database will be built to store and organize the collected data. Subsequent to that, the material recognition feature can be developed. That is all from me. Thank you for your attention.